Welcome back, everybody. This is AP Chemistry, and we're now in Unit 10 and dealing with gas laws. Gas laws are something that we cover in general chemistry as well, so this first couple sections actually should be pretty good review for us, just to see how it works. Today we're going to be taking a look at Section 1, which is working with the ideal gas law and also the combined gas law and the components in there. So we're going to start with those things and just seeing how when we're dealing with gases, we always take a look at volume, temperature, pressure, and the amount of material, in other words, moles, are all going to be affected by that. Okay, some of the things when we deal with ideal gas law, we got to keep in mind when we're talking about volume, we're always going to be referring to liters. Our temperature always has to go into Kelvin, and then typically, when we talk about the pressure of things, we're going to be putting it in atmospheres or torrs. And sometimes when we're collecting data, we'll be collecting it in millimeters of mercury. We'd also might be collecting in kilopascals. So we're going to be taking a look at how some of those things work and some conversions in there. Now, if I'm dealing with the ideal gas law, what that's doing is actually doing some conversions for us, putting things into standard conditions for us. And so that's where some of these types of calculations might come in handy for us. All right, so the ideal gas law is a correlation of pressure. Now, this must be in, for our values to work, must be in atmospheres or kilopascals, okay? So that is a must. You got to convert those. This volume must be in liters, okay? And this will be the number of moles. And the reason we're doing, and I should probably just put in a reminder that this must be in Kelvin, okay? So remember how to do that. Now, if we're going to be putting everything in these units, then we can use our value for R. And for us in AP Chemistry, our value for R will be 0.08206, okay? That's if we're in atmospheres, if we're in liters, if we're in moles, and if we're in Kelvin. That's where that value will come in. Now, what we're doing with all of this, we want to back up to see how these things are all related. If we take a look at the volume of any gas, well, that is going to be proportional to the temperature. This symbol stands for proportional. Okay, and so if we take a look at that, so as the temperature goes up, the volume goes up. As the temperature goes down, the volume goes down. Okay, now if we take a look at a gas and dealing with that, let's take a look at pressure. Well, what we see is that they are inversely proportional. And so if I add pressure to this, my gas is going to go down. If I reduce pressure, my volume will go up. So that's what's happening there. And then kind of a no-brainer with this one, if we take a look at the number of moles as we add more things in there, then we're going to be seeing that it's going to add to the volume of that as well. Okay, so those are the relationships we're going to be taking a look at with this. And so let's just put some of these into action with some problems. Okay, let's take a look at hydrogen gas, and we just want to take a look and do a snapshot. Nothing's changing here for conditions. We just see these values, okay? So if I plug it in, and I'm going to use the phrase PIV-NERT a lot, PV equals nRT. Let's just plug in our values for this. So I have 1.85 atmospheres. I see that I have 8.56 liters. And let's see, we're solving for N. And so my R value is 0.08206, and here's the only one that we had to convert over. It's in Celsius, so that's going to be 273 Kelvin. Okay, so then I just solve for N. That ends up being 0.57 moles. I could certainly figure out, since we know what the gas is, I could figure out in grams. I would just multiply that by 2. Problem isn't asking for that, but you can see what we can do as a type of kind of permutation to the types of questions. Okay, so that's the first one, taking a look at the ideal gas law. Okay, we can take a look at combined gas law. This is section 1 and 2 together, because section 1 is pretty simple. Section 1 and 2 together, taking a look, and we see Boyle's law is now changing conditions. And that's the thing that I want you to notice is we're changing conditions of things. And so the question is a little bit different, saying what happens when I do something. So what's happening in this problem, if I was going to put it into a story problem, we have what pressure would it take to move from 8.56 liters down to 1.35 liters? If we started at 1.868 atmospheres, what would the new pressure be? Notice that the temperature is held constant. Okay, so that's what's going on in this type of problem. And so this is an example of Boyle's law, which I see pressure and volume. Now remember, we already know some things about this, that as I am reducing volume, my pressure must be moving up. Okay, and so that's just my prediction with it because they're inversely related. So keep these units kind of straight, and I see 8.56 times my 1.68. That's going to equal my 1.35 times my x. That will be my new pressure, and my new pressure was 4.9 liters. Did that follow what I was expecting? Well, I started at 1.68, and yes, indeed, my pressure went up. Okay, so it follows the prediction with there. And do in this section, take a look at your significant figures. Okay, that's going to be a key. Now, there's another relationship we can look at, and that's going to be with Charles' law, which is volume and temperature. Notice we're keeping the pressure the same, and the temperature is going to be changing. Okay, so notice that these are going to be directly related. Okay, as my temperature goes down, so should my volume. Well, here my temperature is going up, so my volume should go up. Let's prove it. Okay, so my first value is going to be 3.8, and that's in liters. Oh, but watch out, this is 5 degrees Celsius. So I add 273 to this, and so that ends up being 278 Kelvin. Now that's going to equal then my V2, so that's what we're solving for. And my new temperature, I add 273 to this, and so that gives me 359 Kelvin. Okay, so my V2 ends up being 4.9 liters. Did that follow what I was thinking? Yes. Okay, so I know that I did the problem right just because of those. Again, watch out for your temperatures. Okay, now let's look at Gay-Lussac's law. Gay-Lussac's law is a little different variation, taking a look at pressure and temperature. Now be careful because previously I was looking at volumes, right? And so what happens is if I heat up a gas, that's going to create more pressure. So I would expect these things to be, as one goes up, the other goes up, I would expect them to be also directly related. So if I keep the volume, and this would be like in a metal canister or something like that. If I could do that, I want to do what my new pressure is. If you look on the side of a shaving cream can or something, they say, caution, don't store above a certain temperature. That's why, because we want to take a look at how much pressure is being amassed. All right, so let's add my 273 right away. I see that this is a 278, and I add 273 to this side, and this ends up being 359. Okay, so let's plug in my values and let's see what we get. I end up with a 1.5 over my 278, and that will equal my pressure now over 359. My new pressure ends up being 1.9 atmospheres. Did that go up? Yes, it did. Okay, so then I would be pretty comfortable that I did the problem correctly. Okay, now we can combine all of these together. Okay, the combined gas law takes a look at Boyle's law, Charles' law, Gay-Lussac's law all together. And we can see if we're changing several conditions at once. And again, with these versus your ideal gas law, we are changing conditions. Okay, so I see that my volume is what I'm looking for. My pressure is going down, and my temperature is going up. So I've got a couple of things that are working together. So let's see, this is going to be 273. And this is going to be 283. Liters, atmospheres, everything checks out. We're in good shape. Let's plug everything in, and I see that I have 1 atmosphere, times my 3.4 liters, and that's divided by 273, and that's going to equal my 0.7. Looking at this side, 0.7 times my V2 over my 283. Okay, so V2 then would be 5.0 liters. Okay, so what happened is my temperature went up. That would cause my volume to go up. What happened is my pressure went down. Well, as pressure goes down, volume goes up as well. And so that's what's going to happen within those. They might be asking on an AP test to predict what would happen. And so that's why we want to really hold it to those standards. Now, we can notice that in all of this, we've not really factored in the number of moles. So let's take a look at Avogadro's law. Avogadro, remember 6.02 times 10 to the 23rd, that's how many particles per mole. Well, Avogadro's law can be applied here to the number of particles. So we see that they are, again, directly or proportionally related, because as I add more particles, that's going to add to the pressure, that's going to add to the volume of things. So let's just plug them in, and this is pretty simple. Notice that my temperature is changing. Let's assume in this one, I think this is a mistype. This one's going to be actually 5 degrees Celsius for this one. We could factor in with some of those others if we wanted, but let's start with this, okay? So we're seeing that we're going to be taking 5 degrees Celsius, so that's a non-factor. We have 2 atmospheres, that's a non-factor. I see 0.5 moles. So we have 2.5 liters divided by my 0.5 moles. Okay, that's going to equal V2 over 0.75 moles. Okay, so my V2, I see that I end up with 3.75, and that's going to be liters. Okay, so as I add in another quarter's worth of moles, I add in a little bit more in terms of volume. Okay, now with this, we could factor in temperature. Just remember where temperature goes in all of this. We could have gone T1 and we could have gone T2, and we could have factored in those as well. So that's not a problem. It fits all in just as easily. And guess what, guys? That is it for this section. All we had to do is see how to apply those different things. Watch out for your units, and you should be in pretty good shape. Good luck.